Hello. In our previous video, we introduced the topic of vector databases. In this video, we'll look into a bit more depth about how these work. In our last video, just to recap, we established that we take some kind of data, can be structured, unstructured, any kind of data, can be audio, video, anything like that. And then you use an embedding model to create some embeddings of the data like that, like a series of numbers, and then you store it in the vector database. And an application or anything can query these results and find whatever is close by it. So we talked about bucket-based search. That is one way to do the search. There are several other ways too, which we'll look into in this video. That was just dividing the whole thing into buckets, like the vector database into buckets, and you see a centroid, like the closest one to our query vector. So the numbers which are closest, and once you find out which bucket it is, you can just search whatever is inside. So you don't need to like go through all of the database. You can just search within that bucket. All right, I also need to give you some clarity on what the vector index is and what vector databases differ from how vector databases differ from a vector index. So there are algorithms like the Facebook AI similarity search, similarity search, which is really good at searching and retrieval. It's just an algorithm built for searching. So you have a vector index, as in you store all of these vectors, and then you can just search and take it. But it's not very complicated and it has not that many advantages. It's just a direct algorithm. But a vector database is something built to manage this data, like how it is stored in a vector database. All of this, how it is managed properly, that is the role of a vector database. And it's more complex than a simple vector indexing algorithm. One of the key advantages is that real time updates. So in a vector index, you might probably need to re-index all the time. Like if you add more data, then you probably need to find the index of that, add it, etc. But that's not really very good in real-time applications where you need to update something and see it then and there. So in a modern vector database, that's probably going to take you the order of 2 seconds to see the change. That is going to be very difficult in the case of vector index. So basically, there are a lot of optimizations in this. And it's more complex, as in there are more features to it. So there are things like metadata filtering. So even if you're searching for a particular data in a vector index, let's say, and if it's like directly similar, then you might get it. But what if you want to search something with the metadata? So, for example, if it's about a book, what if you just want to search about some author or something related to the author? And there are things associated with the data, and there is some kind of a pre-filter, post-filter, and you can just filter using the metadata in a vector database. Also, there is, of course, added security because it's should be used in production level systems directly and as a database. So there are a lot of security features associated with vector databases too. And also we can scale it quite easily. All right. And if you've forgotten how the bucket-based search worked, I'll just give you a quick recap. So we already established that, let's say if it is the data of pictures of a lot of fruits, maybe a lot of fruits like let's say apples and are all clustered together in one place, and maybe something like peaches are here, like let's say these are apples and these are like peaches. Okay, I'll just use yellow for now. Okay, these are all grouped together, and then if you want to search a particular thing, you'll first see the closest bucket. Since we're dividing the whole vector space into several buckets, and you find the nearest bucket. And also we use some algorithm, any clustering algorithm, and mostly we use KNN in this case. That's K nearest neighbors. You just find the nearest neighbors and you find the centroid too, and then whatever is near it. Similarly, we find the query, which bucket it belongs to, and in that bucket, once you figure out what bucket it is, you see whatever is closer to it, you search through it, right? And that's a simple bucket based search. And in this figure, it's even more clear that this grayed out part, this shaded part, that is the cell we got because the query vector is here. And there's a centroid of this vector. So this is the centroid of this space, this cell, anything, this bucket, whatever you want to call it. And if you query something, you'll see what centroid it's closer to. It's this bucket. And then you just search through in this bucket. So we'll need an algorithm which is like quite fast. That if you're retrieving something, it should be quite fast. So sometimes what happens is if you go here, if there's a lot of data in this bucket, it might take a bit more time, and we also need it to be very accurate. So this is still used, but there are some other algorithms also we can look into. Right. Another algorithm is HNSW, which is right. Let me switch the color up. With hierarchical navigable small worlds, HNSW. This is related to graphs. So let me give you another illustration here for a quick intuition so that you might. Okay, so let's say it's a graph which is disconnected. It's like a circle, right? And then you want to get something which is closer to this. So when we are searching, maybe what we can do is we can just start here, go here, go here, then go here. And then you can see this is close, right? So you can just take a jump here. Otherwise, what would happen is you'd probably want to like take several steps, right? If it's a connected graph, you just go throughout and then finally you reach it. That's going to take a lot of steps. So this is the, what do you say, this layer, right? So if you take this layer and this is the like target you want, you don't want to like start from some, like you want to start from some place and go around the whole graph searching for where your thing is. So what it effectively does is create some kind of shortcuts. See, so if you just like if you track the blue, and don't worry if this figure is not clear to you, I'll show you better figures. So this is just in case this is just in case if you find a quick understanding, that's good because you'll understand the rest of it better. But that's all right. We'll just go into more details about it. So it's basically a multi-layer graph structure. And some of these layers are just long connections, and some of them are short connections. So we won't just directly go into the short connections and just search it up. Rather, we'll just see. So it's sort of like in a binary search too, but it's very far from that. But still, so if you want to see if it's a sorted list of 1, 2, and 10, and you want to search for 10, you just divide it into two, and then you see, okay, this is 5. It's less than that. So you just remove all of that. You divide it again, you remove that, and then you see you get 2. So it's just you got that in 3 steps, right? So it's pointless if you like, let's say if it was 8 you want to search for, and you go from 1 2, and it's going to take a lot of time, so we don't want to do that. All right. um it's simple intuition about that. So yeah, so what it does is it's just this greedy routing. That means that it enters a place, all right, and then it wants to go to your query vector, right? So it just goes to the most nearest neighbor, like in the outermost layer, which is the long connections layer, and you try to reach as close as possible, and then you try to reach the vector. Okay. So there are high degree vertices and low degree vertices. In some layers, there is like probably low degree vertices. So you start where there are a lot of long connections, and then you go down until you find the vertex which has probably your data element 2 connected, your target vector. I think this gives you a better intuition of it. All right. Okay, I'll go here and then I'll go there again. All right. So you start at the entry layer, and probably there is just one or two. So you can just go in between that. So let's say if your target is somewhere here, you'd probably go to this vector, and then you'd probably go close to this vector or something like that. And then you finally converge on something there, right? Um, so it's basically to have some kind of skip connection so that you don't have to go through the whole data. Yeah. So if this is your target vector, just go there and in the next layer, and then you realize it's closer to this. So you go here, and then from here, you can just directly reach the target vector just in 3 steps. If in case you are going to enter here, it's going to it's going to be more difficult if it's like a huge data set, because you'll have to have all of that processed at the same time. But you have simplified version of the map, let's say the map of where the vectors are. If it's very simplified, then it's easier to compute and it's way more faster. um Let me take another example. So let's say if you're looking for 11, this picture is directly from the Pinecone documentation. Pinecone is such a vector database, which we will learn about in our next video. We'll just try to create a database and do things with Pinecone in the next video, but we'll save it for that. So yeah, um, so you go to the entry layer and you go to 5 and then you overshoot, right? I just go beyond it. Like it's a sorted list. Let's say it's a sorted 3, 5, 7, 11, 14, 21. So it overshot, right? So you just go here to the next layer in where 5 is stored, and then you go to the next node, it overshoots yet again. So you go down to the next layer, and now you go ahead and then you find 11. Probably if you're going to look for 7, you'd probably have to go another layer. Or maybe if you were going to look for 14, then probably you go down here, right? Where's yellow? Yes, and then you'd get 14. That's if you're looking for 14. You get 14. And that would take you to the last layer. So sometimes you don't even need to reset. Probably if you're looking for 5, you just directly get in this. But that's not that important. All right. So this is another algorithm, and people are still trying to like find the best way to do it, like so that because compute cost is a huge problem, right? So we discussed about what LLMs has an issue with the context size. So even something like GPT-4o has only a 128K context length. That means that it has 128K tokens. That means pairs of words or entire words around that much. But that's not enough. And even to use 128K, that's gonna cost a lot for 1 million tokens, right? It costs a lot to run the whole model too. And we don't want to give all of that to. So what we do is we augment it with the database, external database, which is a vector database because it's like queryable directly using vector indices. So if you want to find some context which was there before or something similar which was there in some other book or anything, you don't need to just give the whole book to GPT-4o in its context length, but rather you can just query it, what is closest to it, and then you can take it. It's quite advantageous. But at the same time, you want to have it as efficient as possible. You don't want to add to the overhead of GPT's inference. So, like even if you have some kind of fine tuning or something else with a large language model, and you're adding even more delay to that, and then if you have a bad vector database to work with it, and I mean using RAG, then it would create even much more delay. So you want it to be very optimized. Most use cases, and especially in real-time databases, using vector databases. All right, so I've been telling that we have one vector here, and then we have your target vector here. So how do you know how close this is to this, right? I mean, it's intuitively you can just see it, but how do you calculate it? So there are several ways to do that. One of us is just the simple Euclidean distance, that is x2 minus y on the whole square plus y2 minus y on the whole square, and then you'll just get the distance, right? You just take that, and you'll get the distance. That's the. It's pretty simple. You just try to minimize this whatever is the least, whatever has the least Euclidean distance. That'd be great. But that doesn't always work because it's not a Euclidean two-dimensional or three-dimensional space, right? It's not a simple space. It's much more complicated than that. It could work, but we could also use different things. And one thing is the cosine similarity. So you just take both vectors and you see how close they are to each other. So if they are opposite to each other, they'll be like you have -1. So if it's like orthogonal to each other, it's probably 0. And if they are likely aligned together, then you'd probably get something like 1. Just take the cosine. So it slightly works with more. Uh, it still depends upon the use case, but this is one way you can do that. This is one way you can do that, and one is just the dot product, and that is just a dot b by mod by into b mod. That's all right. Cosine distance, which we already talked about, and this just the dot product. We just go through the whole thing and you just directly take the whole dot product. And if you take the dot product, whatever is aligned together, something which is like that will have a higher value. And like just like in cosine similarity, if it is like orthogonal, it will have like lesser values. Yeah, there are other ways too, but we don't need to um, go to that. It's just a main target is to find the distance between those two. Right? All right. All right. Now let us talk about optimization. Okay. There are several ways where, like I said before, optimization is very important for vector databases for its particular use cases too. The most optimized vector database would have the most use because of saving compute time, which is a huge problem right now. Because LLMs take up a lot of compute. So we cannot afford for our vector database also to take a lot of compute. So you need to optimize it as much as possible. And one way is this quantization. So what you do is we have the whole thing when we divide all of the dimensions into small, small, small pieces. And each of them has its own centroid. And then you have a compressed representation. There's several ways of giving a compressed representation. So if you have, let's say, this amount of data, and then you can just send it through a small neural network, and then you train it. And even if this has a lesser dimension, it would still, in essence, have an understanding of what kind of data is, maybe like a simplified version of it. So this can be used to query this back. We can do things with this too, right? We don't need to like directly go through all of this data. So this is one way you can just segment it. I don't want to go into the exact details of how it is, but this is what it is being done. This divides it into each um, like 128 segments in this case. So it's like 128 into 6, right? Each of them have 6 dimensions each. And you represent one segment with its centroid. That means like if it's, let's say, one random segment, so you'll just find its centroid, and the other one that's its centroid. And yep, that's how you have a compressed representation of it. This is 128 bytes, right? Compared to 3072 bytes. So this kind of quantization, this is a very simplified version of it, but this quantization helps a lot to have the storage issue sorted, the compute issue sorted. Um, All right. The other thing is caching. So you might already know about caching, like if you're from the computer science background, but even if you're not, let me just give you a quick recap. So caching is simply something which is done even in your browser, right? There are some things which you take or use a lot, like back to back, and you don't want to go to either your hard disk, right, or your RAM. And each time your application asks for something, you want to go to your RAM, you want to take it, and then it goes. So right now the bottleneck here is this RAM read write speed, right? This bus, all of this, that is what comes into picture. Like maybe RAM is relatively fast compared to your like hard disk storage, etc., but it's still slow. Like even if you want to take something from your hard disk, it's going to be very slow relatively. And maybe some actions need to be done a lot faster, especially system processes and things like that. And even in your browser, if you're running maybe like a React web app or something which is like more resource intensive, there's a lot of graphics and all. Even if that's not there, and if you want to like boost the performance, what you do is something called caching. You introduce something here, like as an additional layer. You introduce an additional layer. So what you do is if you want something, and this is very very fast, it has a very low size, maybe like it can be a 128 KB cache too, right? Maybe this is rather, I don't know, like 16 GB gigabytes of RAM, and this is probably 1 terabytes of hard disk, but it's just 128 KB because we just need that much. And whatever is most important, whatever is accessed a lot, there are a lot of algorithms to cache too, but um, simply put, just whatever is most used is the stored in cache. All right. And if you don't find it in the cache, what you'll get something called the cache miss. So you get a miss. Now you'll go and look into the RAM. And if you keep on accessing something from the RAM and it's not in the cache, what you do is you take it from the RAM, you store it back into the cache. So now we can just access the cache much more easily. So cache is just some easy access things. Oh, in a better example is some people tend to do that is like if you have a lot of clothes and then you have a wardrobe and you've stored all of your clothes in your wardrobe, you have it very organized as in you have all of your t-shirts here and all that. But then also like there are some clothes which you wear quite often. So what you do is you just, some people tend to just put it on a chair, like you just have all of your recently used clothes on a chair. Otherwise, you just use a hanger. I think that's the right way to do it. You just hang it on your hanger, which is like quite easily accessible. So whatever you access commonly, you take that. And maybe later on you decide, okay, this shirt I don't want to wear so much. You just put it back. And then you take another, like maybe something you knew you got, and you put that in your cache storage so you have easy access to it. All right. Yep. So you have the database, and then you have a cache. So the application first asks for the cache, and if you miss it, then you'll go to the database. Otherwise, you just have it in the cache itself. So yeah, this is just an image of the geometric partitioning of the vector space, right? Like earlier, I said that we put it into buckets, right? And it's done geometrically, as in whatever vector space we are in, we just draw lines around it. We just draw boundaries about it geometrically, and this is the centroid. What you get from there, right? So when you have a new query, what systems like Pinecone does is it has something called a freshness layer, because freshness is something which is very important. Like I said before, Pinecone, for example, gives takes 10 seconds sometimes. I mean, 2 seconds sometimes. This is when you have some little amount of data. Maybe it's not true when you have a bulk of data being stored. I'm talking about a maybe like new entry. Maybe I bought a new product of an e-commerce website and that needs to be stored, just my information. That'd be very fast. But then you don't want to re-index, right? So I already discussed what indexing means, which is like you take the data and then you run it through an embedding model and then you find the embeddings and then you store it. And that's probably, as you can imagine, it's not gonna get done in 2 seconds, especially if it's like a huge deep database. Re-indexing a database has a lot of performance advantages. That means that even if you have a lot of data added, and if you re-index it, maybe it optimizes it in the sense that, okay, it calculates new centroids and all of that, and it will be even much more better and more optimized, rather than like having all the other data intact and maybe adding something outside it. You just mix it all up, so it'll go to wherever it is supposed to go to its similar data entries, right? So you add a query, and what they do is they add something called the freshness layer. So it is something like a cache. So when you add a new data, it just goes to the freshness layer. So when you search, they'll just first search for the freshness layer. So maybe like after a while, what they do is they will, in with time, add whatever is there in the freshness layer. Like let's say this is the ocean and this is a small river, and you can use stuff from the river, but in the end it just goes to the ocean and then it just gets mixed up and it's all together. This is your whole vector database ocean, like whatever is there, like all of your data, it's like indexed very well. And then if it's not in the freshness layer, maybe like some old data, then you can just directly access it. Maybe you search there, then you just find whatever is there, and if it's clearly that nothing is there in the freshness layer and maybe something's better here, you just take it from there. Yeah, and as it's written here too, like it is like new data is added here too, but it's gonna take some time, like to reindex. You don't want to just reindex every time you add some data. So that's why some small things, and these are the differences between a simple vector index and a database too, because this is just one feature. There are a lot of other things, some we discussed before, and even more that makes it so robust and so good and saves upon a lot of compute too. Right. Mm, so yeah. So in our next video, we'll just go to see applications of Pinecone. We'll actually open up some code. We'll try to get an API key from Pinecone, and we'll try to create a database. We'll do some fun stuff there. I hope you have a good idea of like how Pinecone works, as in a vector database works, and maybe an idea of what embeddings are and all of that. And most probably, when you use a vector database in real life, you probably wouldn't need to know what algorithm is being used. But the more you know about all of this, it is even better. And even in LLM space, it's really good to know about all of this, like what embeddings are and what vectors are, how it is stored. And even in system like RAG systems, retrieval augmented generation systems, is one of the frontiers of large language models in AI right now. And you'll have a more thorough understanding of what it is. So I will include a link to an article in the description, and you can go read through that too. Like if you want to know more about it, if you want to learn more about particular algorithms too, you can do that. But I hope you got a good overview of what it is and how it works. Yeah. So one final recap: you have source data. It can be multimodal, like images, text, anything. We have an embedding model. So the application asks the embedding model to like a query, because, and then you get maybe this is like the query vector and this is like the embedding, like both of that, right? Even the source data is converted into a vector embedding, and even whatever query we are adding, it's still going to be converted into a vector, because you will need to compare both of them together. And then you have the vector database, let's say Pinecone in this case, for example, and then you give the results. You do some processing again, because it's just a vector value, or maybe you need to do even more processing if it's just metadata and things like that. Then you get back to your application. That's it. And of course, you have other things like freshness layers and all coming in between. But yeah, this is in essence what happens in a vector database. All right, I'll see you in the next video about how Pinecone works. We'll have some fun in that video. Thank you.